Right. So today we're happy to have Karim Shaheen. He is a second year PhD student in the group of Michael Buchholz at the University of Cologne. He did his undergrad at the University of Trieste in Italy, and also a master's in the same university. And he is currently working on mainly on measurement-induced phenomena. In this case, he's going to tell us about this in the context of free fermions. So, thank you.
Right. Thank you for the introduction. What I would like to talk about today is partly in this work with Michael Buchholz at the University of Cologne, but mostly it's about newer developments, things that we're working on these this kind of this model. And I would like to start with a somewhat fundamental question. So measurements are typically something that you do at the end of an experiment, right? You start from some initial state, you perform some evolution, and then you want to characterize your final state, and you do this with some set of measurements. And in this view, measurements are something passive, and we're not really that much interested in how they influence the system itself. But now, for me, a natural and somewhat fundamental question is, well, what happens now if measurements and the unitaries are intertwined in this kind of hybrid type of dynamics? And here, this is just a discretized version. And this is interesting for a number of reasons. For example, if you're interested in state preparation, you can do this much more efficiently if you have measurements as part of your protocol. But to me, at least, this is also interesting from a kind of more fundamental perspective. And that's because this kind of dynamics now implements competition between the unitaries and the measurements. And whenever there is a competition, this should kind of tickle us because from a critical phenomena point of view, this opens up the possibility of having novel phases and phase transitions, where now these are dynamical in the sense that they appear in the steady state properties of this dynamic. So not in the kind of ground state properties of a system because we don't have a Hamiltonian here, and neither in the kind of classical sense of a competition between energy and entropy. So what is this competition that I'm talking about? Well, on one hand, we have the unitaries. These could be, for example, fermi liquid Hamiltonian or random unitary gates. And the steady state configuration that this favors is a configuration where degrees of freedom are essentially delocalized. And there is a buildup of kind of correlations, but the keyword here is that there's a high degree of entanglement. And this is opposed to measurements, which kind of typically these are single particle measurements. And these instead favor a configuration where degrees of freedom are localized. And since measurement extracts quantum information for the system, it reduces the amount of entanglement. And what was realized in a kind of paradigmatic model a few years ago is that now we can take this kind of setup where now we have these measurements happening with some probability P. And this is kind of, you can take fully random gates, but also kind of a Fouquet type of dynamics. And what you see is that you can get a phase transition in entanglement content by tuning this probability of measurements. And you get a phase transition from a volume law of phase, just highly entangled, to an area law of phase. And here we measure the amount of entanglement through the von Neumann or entanglement entropy between some subsystem A and B. And in the volume law phase, this entanglement scales extensively with the subsystem size, whereas for the area law phase, this simply grows like the surface separating the two subsystems. And so in this case, it doesn't really scale at all. And so this was kind of a pragmatic model, and much is understood for this. But now I would like to present a second kind of example, which is a bit closer to what I would like to discuss later. And that is a continuous version of this in a sense, and a natural also application. So let's take now a 1D chain of free fermions plus measurements. And then in this case, we're measuring the fermion density in each lattice site. And these measurements are happening with some probability or rate gamma. And again, we have a competition in the steady state properties that these two kind of objects favor, and also in the entanglement content. In this case, we don't really get a volume law, but the kind of signature of a metallic state is instead of logarithmic scaling. So this happens whenever you have a Fermi surface. And although this sounds kind of like a simple model, right? It's free fermions plus measurements. It can really get simpler than that. It has turned out to be quite tricky. And there are essentially two descriptions available for this problem. And this kind of duality of how you can describe the system will come back later on. But essentially, so one description predicts a BKT type transition at some finite rate of the measurement strength. And this is opposed to instead a weak localization picture, which predicts no transition. And in both cases, things are kind of made more complex by the fact that there's both kind of numerics are hard due to the fact of an exponentially divergent correlation graph in both kind of scenarios. And this is also what kind of people have seen. And kind of now the dust kind of seems to be settling in favor of this weak localization picture. And the reason why I'm bringing this up is that this is kind of, it's interesting to understand why, and this is somewhat indicative of a deeper connection between d-dimensional monitor dynamics and d-dimensional static disorder problems. Indeed, kind of this duality between plane waves and localized wave functions have reminded some of you some kind of classical example of kind of condensed matter physics problems. This is the competition between the Hubbard model, but especially relevant for this kind of topic is Anderson physics. And what's the picture here? Well, and this can be made quite concrete, but the phenomenological picture is that these measurements, which are random kind of in space and time, and they are random in a twofold sense. So they are both kind of in a random position, but also have random measurement outcomes. These act kind of effectively much like a static disorder potential. And this is the setup of the Anderson model. And just as a quick reminder, the Anderson model is just a model of free fermions on a lattice plus a quenched static, so a quenched random disorder with some strength W. And for dimensions 3 or higher, you get a phase transition from a metallic to localized phase. And we so this is kind of just a flavor for the phenomenology, but this can be made quite concrete. And it is by virtue of this kind of link that it is argued that the 1D problem has no transition because the 2D Anderson model doesn't. But in this view, then the 2D problem should be interesting, right? Because this now is linked to 3D Anderson physics, and this does display a transition. And what I would like kind of to convince you is that in the following kind of minutes is that while indeed there is this connection, probably this picture is not concrete, and there's more kind of to it. So now let me briefly be more specific about how we do implement these measurements. So you can do projective measurements, which is kind of this is the more well-known scenario with some probability P, for example. But what we work with is instead continuous or weak measurements. And this makes analytics a bit simpler. And the idea is quite simple. So let's say we have our system and we want to measure some observable O. So in our case, the fermion density on each lattice site. We can couple this to some meter described by some conjugate variables x and p. And if we initialize our global state in a product state, we can now couple the system and meter with some coupling strength gamma. This will ultimately be the measurement strength. After some time, these will be entangled. And now by performing a projective measurement on the meter, we can gain partial information on the system. So this is somewhat less destructive on the system and allows to treat kind of these measurements in a more kind of continuous manner. And after this projective measurement, we get a product state again. And now the kind of action of all of this is all captured by this generalized projector acting on the system. So now this kind of allows me to introduce our model, which is the following. So we have an L by L half-filled square lattice with just a free fermion Hamiltonian. This wants to delocalize particles and wants to delocalize quantum information as well. And we implement these measurements through this kind of generalized projectors. This instead wants to localize particles and quantum information. So now these are kind of our two dynamical ingredients, and we can work with them now. And I will now discuss briefly the analytics without going too much into the details. I want to just kind of discuss about some highlights of it. But what's the kind of first idea? Well, now we have an open problem, so we cannot really we don't have a Hamiltonian. And the goal ultimately is to write some form of quantum master equation to describe the evolution of the density matrix. But we also have noise, right? Because we have these measurements which kind of have random outcomes all the time. And so we'd also like to make some appropriate averaging. And we would like to look at the state at kind of long times because this is the steady state solution. But exactly this object, so the averaged long time density matrix, it turns out that as soon as you turn on noise, this will just kind of become the infinite temperature state. And what does this mean is that all simple observables, which are all objects linear in the density matrix, these are all trivial. These are insensitive to what's happening in the system. And this also justifies the use of the entanglement entropy because we need nonlinear quantities in the density matrix to see any type of physics. Now, the idea is to borrow a trick from statistical physics, which is this replica trick. And there, the idea is to reduce the problem of computing the log of the partition function average, so the average of it, as a problem of computing the average replicated partition function. And this is also what we do. So essentially, what we work with is a replicated density matrix. And with the two dynamical ingredients that I showed before, we want to write down a replica quantum master equation. And the details of how we get this are not too important right now, but I do want to briefly discuss its structure. So what we get is this equation right here. We have this unitary part and then this measurement part, where R now is the number of replicas, and these objects are summed over the replica index. And this lends itself to a nice intuitive picture because now on each lattice site L, there's a collective kind of big spin, collective coordinate emerging, and we can describe, we can interpret each term of this replica quantum master equation as doing some rotations um, on these spins. So the blue term, this is the Hamiltonian part. This is a side exchange term. This favors a plane wave configuration, right? And so this wants to push all the spins to the equator. Whereas the measurement terms, this purple and red ones, they want to synchronize all replicas and push the spins to the poles, which are the only configurations where you would get a localized wave function. So now, we can see also at this level this competition between unitaries or the Hamiltonian and measurements, and this is now the starting point to perform analytics. And here again, we get a sort of kind of dual approach possible. So how does this look like? Well, the first approach is this Anderson-like kind of approach that I discussed, and this points ultimately to Anderson physics. And I, again, won't go too much into the details of it, but I want to briefly discuss some features. So the idea is to approach this in a filteretic kind of Keldysh approach because it's an open problem. And the fermionic action that you can write down looks like this. And this really looks a lot like what you would get for the 3D Anderson model with some caveats, namely that now we have a space-time local structure. But more importantly, there's this extra kind of sigma x acting on the space and Keldysh coordinates that this is not present in the disordered problem. And this quite kind of it's not really trivial that this happens, but this is responsible for giving us an emergent space-time invariance in our problem. And what this ultimately means is that if we now kind of massage a bit this problem, what we get is an SUR model in an effective D plus one dimensions. And this is really there are a lot of similarities with Anderson physics. There's probably someone in the audience who is even more experienced than me on this topic. But the idea now is that this approach is what gives you the link to Anderson, and this points to one parameter scaling theory. It is by kind of virtue of this argument you can perform this for the 1D problem as well, kind of the same approach. And by virtue of this, you would argue that there is no transition. But you can also go kind of another way, just like the 1D problem, which is what I call a Hubbard-like way. And you can realize that this was realized really fairly recently. But what you can do on bipartite lattices, which is our case, you can perform an exact unitary transformation from the replica quantum master equation to an effective Schrodinger equation with a non-Hermitian Hamiltonian, which is a Hubbard-like Hamiltonian. So there is this interacting term, and this is kind of a non-Hermitian Hubbard-like model in 2D. And while the implications of this are yet unclear, what is clear is that this now points to a model with an enlarged symmetry and in D dimensions. And while on one hand we have this kind of one parameter scaling theory physics that this is pointing to, on the other, this is pointing to Hubbard physics in 2D, which probably of all the phase diagrams I can think of is one of the most kind of complicated. And this kind of sums up what I wanted to say about the analytics. So this is kind of the standard approach in a sense, but there seems to be somewhat more, although this is still kind of unclear. And now in the following, I would like to kind of show you the numerics that we did and kind of support this picture. So kind of support the idea that there is a link to Anderson physics, but maybe also something more. So are there any questions up to this point? Well, in any case, you can stop me to ask questions. Okay, so I mentioned that entanglement is important, right? So let's look at the entanglement content. And what you typically look at is you take your system, you cut it in half, and you measure the amount of entanglement between your half system cut and the rest. And one other useful probe is the mutual information between two subsystems A and B. And this kind of is a measure of the amount of entanglement between them or kind of the correlations between them. And this is what we see in our case. So in the inset, you can see the entanglement entropy divided by the linear system size L, and this is in a semi-log scale. So these blue lines for weak measurements are the signature metallic scaling, so an L log L scaling. Whereas for the strong measurement case, we get this area loss scaling, which is L. And with the mutual information now, we can detect where this transition is happening, and it seems to be happening at around gamma equal 5. And kind of if this was a one parameter scaling theory, this would probably, the story would be over in the sense that we have probably found now our localization transition point, and there's probably not much else. But as you can probably guess by the fact that I still have a bunch of time, we do find something else. And this comes up if you look now a bit more closely into this logarithmic scaling of the entanglement entropy. So we know that for weak enough measurements, we get this log scaling with some prefactor C of gamma. And quite surprisingly, this also displays a size independent, so a scaling variant point at around 2.15, and with a very sharp kind of crossing point here. And this is kind of a bit surprising. And to more deeply investigate this, what you can do is that instead of looking at just as half system cuts, in this case, you would take a half system cut and just increase the system size. Now you can fix the system size and look at how entanglement scales with the size of your subsystem. And there are many different geometries you can take. This is kind of a natural choice. And what we see here now is that the scaling of the entanglement entropy with the subsystem size is not really something random, but follows the by now celebrated Cari-Calabrese formula for a conformal field theory. So, and this is really not really expected from the Anderson physics approach. So exactly at this 2.15, the entanglement entropy follows this formula, suggesting that there might be an emergent symmetry at this point. So already at the level of entanglement, we have kind of some puzzling result. But now let me kind of bring forward another one, but also more importantly, maybe make a connection with Anderson physics, also in our numerics. And the way we did so is by looking at a striking feature of Anderson physics, which is probably a bit less known, which is the multifractality of the single particle wave functions. So for the 3D Anderson model, we know that there's a transition from metallic to localized phase. Perhaps a bit less known is that exactly at the critical point, the wave functions are neither metallic nor localized, but are multifractal. And I have depicted them here with a snowflake, but the idea is really that, in the sense that you can attach a fractal dimension to them, and they act kind of a bit strangely, so they have this weird shape. You can capture this with the IPR or image participation ratio, and more specifically with the multifractal exponent, this quantity here. And this is equal to the dimension of your system for a metal. It's 0 for an insulator, and it is fractal, so between 0 and D, and multi because it's a non-trivial function of this moment Q. So how can we make the connection to Anderson physics? Well, it turns out that there are some nice analytical predictions for the variance of this IPR, for what shape it should have for weak and high values of Q with some parameters. And this is our numerical data. So in the left, you can see the multifractal exponent as a function of the measurement strength. we do retrieve the metallic limit, d equal 2, and you can also see that by varying the moment q, we get different values of the multifractal exponent, suggesting multifractality. But perhaps more interestingly is that if we now compare our data for the variance of the IPR with the analytical predictions for the 3D Anderson model, we not only get a match, but there's also structure in the sense that the best match is happening at around 2.15. And this is suggesting that this model is somewhat maximally similar to the 3D Anderson model at this point. And this is also something that kind of it's hard to wrap your head around it, and it was not expected that something like this would happen. Is there a question? Okay. Right. So now we have exhausted kind of the what the entanglement entropy could tell us. We have also looked at single particle wave functions, but we still have this mystery of kind of these two special points emerging with very sharp kind of features. One, and it was the kind of entanglement crossing point, whereas the other had these kind of apparently an emergent symmetry and this multifractal property that I just discussed. So how can we go kind of further? How can we more deeply study this? Well, we can realize that the entanglement entropy is just a single integrated quantity. So this is some functions, sum over O, a function of the eigenvalues of the reduced density matrix. But there is more information available if you're interested in entanglement structure. And this can come in many shapes. You could look, for example, at Rene entropies. But what we are looking at is instead what is called entanglement Hamiltonian. And this is well defined for Gaussian fermions, so systems which are described by a single Slater determinant. And the idea is that for those systems, the density matrix can be, and every subsystem density matrix as well, can be rewritten as an exponential of some Hermitian operator. And this operator is the entanglement Hamiltonian. And it's essentially kind of a Hamiltonian of quantum information in a sense. And before I give you more kind of physical intuition on this, let me just briefly mention that this now is a very nice point of contact between different kind of fields, because this allows you to access all entanglement entropy, the entanglement, the von Neumann entropy, but also all Rene entropies. But this now gives us a Hamiltonian to work with, an effective Hamiltonian to work with. And remember, we started with an open problem with no Hamiltonian, and we couldn't even look at simple observables because they looked boring. But now this gives us a lot of tools. Now we can access, for example, all the machinery of random matrix theory. And this is also not surprising because random matrix theory has often been kind of used as a tool to study localization problems. But we also have kind of wave functions to work with and can look into the eigenstates of this entanglement Hamiltonian. So what's the physical intuition here? Well, essentially, this entanglement Hamiltonian contains information on the structure of the wave functions and not just the quantum information kind of available. And why is that? Well, if we now took a delocalized wave function, the occupation in our half cut, so the eigenvalue of the reduced density matrix, would be roughly 1/2. And this means that our entanglement Hamiltonian has eigenvalue of roughly 0. Whereas if we had a localized wave function, this will more likely than not either be fully in or fully out our subsystem cut, so our cut, giving us a divergent value for the eigenvalues of the entanglement Hamiltonian. And now kind of a little detail is, so I've shown you this subsystem cut, but we have some freedom in choosing which cut to pick. And this is not really the smartest choice. And why is that? Well, if we took the same wave functions that looks kind of half in and half out here, but moved it a bit, and a bit more precisely, kind of a more precise statement is, if we have a finite correlation length, which is not the full system, so still the localized wave functions, but not kind of plane waves, they would have some center, and depending on the position of the center, they could look more localized than they actually are. So what we can do is instead work with a subsystem cut, which has this checkerboard pattern. And this is kind of like taking a picture of the wave functions, but with 2 pixels on one side and with the kind of maximum amount of pixels that are available on the other. And this is reflected in the density of states. So if we take a look at the density of states for these eigenvalues, for a half system cut, so the more naive choice, you can see these very fat tails of wave functions which look localized but really aren't. which look localized, but yeah, aren't. Whereas if we now took this checkerboard pattern, these will be suppressed, and we zoom in on the more interesting kind of area, which is around 0. So this is a bit of a physical intuition behind this. And now, as I mentioned, we can throw at it some tools. And the first of all is looking at randomicity theories probes. So now that we have a spectrum, first thing that you would typically look at is the statistics of spacings, next level spacings, and ratios of them, as well as this R tilde value, which has some kind of nice predictions coming from RMT for an ergodic or localized phase. And what we see now is the following. So in the inset, you can see the R statistics, and we retrieve the two limits quite nicely for weak and strong measurements. And with this R tilde, we not only retrieve the two limits, but we can also interpolate between them. And this displays a very sharp crossing point and lends itself quite well to a scaling collapse, giving us some more accurate predictions of the critical point and critical exponent. And this is a first tool that we can use. I've also mentioned that we can look at wave functions. And the way we can do this is, for example, by looking at this. This is called the Kolbe-Clymer measure. This is borrowed from statistics, where you would ask the question of defining a distance between two given probability distributions. So this is not like properly a defined distance, but is kind of halfway there in a sense. But essentially, in this case, our probability distributions would be the wave functions themselves, and we're asking how much are they overlapping. So this is quantifying the overlap between wave functions, and we're taking them to be neighboring in energy. This means that they probably have the same shape, right? Because this gives us similar eigenvalues. So the idea here is that in the delocalized limit, these were 1 over n, so plane waves or kind of plane wave-like. This ratio would be roughly 1, and the whole thing would be of order 1. Whereas in the localized phase, you can show with kind of some simple math that the scale should increase with system size and then diverge at the thermodynamic limit. And again, this is proving to be a quite nice tool. So you can see on the left, the KL measure displaying the kind of order 1 limit for weak measurements, a linear scaling with L for strong measurements, and a very sharp crossing point. And again, we can get nice estimates for the critical point and critical exponents, which are essentially consistent with the ones we had for the R statistics. So now this gives us a nice picture of what's happening at this point 5. Right now we have an understanding of this being a point, so a localization transition into a localized area law phase. But we still have this question of what's going on at this 2.15. And here now we kind of enter the more work in progress area, or also not the word kind of more experimental, let's say, part of our work. And the idea that we're considering now is the following. So in the 3D Anderson model, what you get is a single point where there's a multifractality of the single particle wave functions. But what if instead what you get in this case is instead of multifractality at a single point, multifractality in an extended phase? And we have not kind of come up with this idea. This has been discussed and debated in the Anderson community as well as the MBL communities. There are also some models of random matrix theory which are a bit cleaner, which display kind of similar things. So what if this is happening? And we also call this an ergodic extended phase because essentially, so in this phase, the wave functions would be still extended in the sense that they don't have zero support. They have a support which scales with the system size, but they're not ergodic, right? Because they have this fractal dimension. And so that's an idea that we want to test right now. And there are a few probes that one could use. I would like to briefly discuss two of them. One is looking at long range correlations in the entanglement spectrum. And because so far with the R statistics, what I've just shown you is all kind of things which relate to neighboring levels, right? But you can also look at the full spectrum and long range correlations between eigenvalues. And another one is a Kolbe-Clymer measure now between uncorrelated wave functions. So the first kind of probe is long range correlations. This can also come in many shapes. One of them is the so-called spectral form factor. And this is a form of two-point Fourier transform that we get here. And again, there are some nice predictions coming from our MT. So in an ergodic phase or delocalized, so in our case, it's also kind of an ergodic GUE phase. So it's a vigoroidal GUE distribution that we get for the ergodic value. So I also call it a GUE phase. This form factor should have a linear ramp and then a plateau. And instead, for a localized phase, this should just simply be flat and equal to 1. And a typical plot looks something like this. This is quite kind of generic. So many problems which are in kind of a clean random matrix theory models, what you get, generally speaking, is this dip for very early times, and then this ramp and a plateau. And what I'm interested in now is this deviation from the GUE limit, right? At some point, we retrieve the random matrix theory prediction for a GUE, and this earliest time after which a kind of the GUE kicks in, this is called the Thales time. And for a perfectly ergodic phase, this would just be 0 because there is no deviation. For a localized phase, this would be 1. And this acts like a measure of ergodicity. So if you have a breakdown of ergodicity, this should measure it. And this is what we are seeing now, but this is still kind of work in progress. But kind of so first of all, we do get the saturation to 1 for strong measurements, meaning that you have a localized phase. It also seems like a nice probe for this transition because it detects kind of a transition happening at 5. And kind of now what I'm interested in is this behavior for very weak gamma. So for big enough L's, what we see is that this is flat up until some point around 2.15, and then this starts to increase. And I'm mostly important about the flatness of it because this kind of gap with 0 can be rationalized because we're taking window averages of this form factor to compute the Thales time, and this kind of shifts the value of the Thales time. Kind of this can be still kind of improved, obviously. But the idea is that so this is an artifact essentially. But what I'm interested in now is that these are flat up to some point and then sharply increase. And while we cannot really exclude for now that this kind of if we added lines for even bigger values of L, this kind of point after which the Thales time becomes non-zero shifts to the right. While we cannot exclude this, at least this is for now compatible with a picture that at some point ergodicity starts to break down. And this might be signaling the presence of another phase. And this is kind of it for the long range correlations for now. And I want to now conclude with the KL measure. And the idea now is to look again at eigenstates of entanglement Hamiltonian. But more specifically, so another KL measure, but now we look at wave functions which are not taken from the same noise realization and neighboring in energy, but this time they're taken from completely independent runs of the experiment or different noise realization. And the idea here now is that so in the delocalized phase, nothing really changes with respect to the previous KL measure. If these were plane waves, for example, this ratio would be 1 and the whole thing would be of order 1. But now things change if we have a multifractal phase, because if we have multifractal wave functions, then these are still kind of extended but have a vanishing support at the thermodynamic limit because they have a fractal dimension. And this means that if we take two uncorrelated wave functions, more likely than not, they will not see each other. And this means that they essentially look as if they were localized wave functions. And so this measure now is sensitive to a transition between an ergodic and a multifractal or localized phase. And this means that if we now see crossing point at 5, we can exclude that there is a multifractal phase because it's just when the localization kicks in. But if we see now crossing point somewhere else, this might indicate that there is a third kind of phase in between. And what we see for now, and still, again, this is also work in progress, but what we see for now is that indeed this KL2 displays a crossing point, but somewhat annoyingly, this is neither 2.15 nor 5. So this is around 3, and we still kind of are unsure of what's going on. So we are in the progress of getting this kind of bigger system size. But what this is now telling us is that it's another clue that there might be a transition and a third phase kind of present in this model. Though, of course, this is still kind of not conclusive and still very much a work in progress. But this is kind of the latest the ideas that we're working on regarding this model. And now I want to kind of recap a bit what's going on. So we have looked into this model of monitor fermions in 2D, and this is to me, it's quite surprising that such a simple model, just like the 1D case, is proving to be so rich. So you cannot really get simpler than this if you want to implement a measurement-induced phase transition in kind of a continuous framework. It doesn't get much simpler than preferments plus measurements, right? But it has proven to be quite rich, just like the 1D case. And we have identified two special points in the phase diagram. One at 5 is clearly kind of more well understood. We interpret this as a localization transition into an area law localized phase, and this is coming from a number of different probes. So this is coming both from kind of entanglement structure, but also this R statistics approach and the wave functions themselves. But we also have these questions about what's happening at 2.15, or generally speaking, in this log phase, where we have indications of an emergent symmetry happening here, this kind of multifractality features, which puts the system somewhat maximally closer to the Anderson model, and indications coming from long-range correlations in the spectrum that there might be a breakdown of ergodicity happening here. Plus, a bit kind of lonely is this KL2 that I just discussed, displaying a crossing point, so kind of a transition here again, but still with question marks about its location. And this now brings me to my conclusion. So we seem to understand what's going on at this gamma equal 5 point. And we have realized that the entanglement Hamiltonian is quite a powerful tool for studying these kind of systems. And through it, we have realized that there's kind of the phenological picture is much richer than expected, especially for weak enough measurements. But there are obviously still more work kind of to be done. So from the numeric side, there is still some work to be done to understand better if there is a stable multifractal phase, or maybe these are just kind of features of some G point where you don't actually kind of land on, but just pass by it. But we also have from the analytics some questions. Above all, this duality between this SUR measurement, this SUR symmetry, and this SU2R one. And with this, now I would like to thank you for your attention. And if you are more interested, you can check out some information here. And I'm open for questions. Thank you.
Very much. Questions? I'm going to start. So everything you described so far was for free fermions, is that correct?
Yes, free fermions plus measurements.
Right. So do you have any intuition for what would happen if they were maybe weakly interacting?
So if they were interacting, didn't hear well.
In the perturbative limit, where they're weakly interacting, or?
Not much is known about what happens if you add interactions. So one thing that could happen is that you might now get a more highly entangled phase instead of this logarithmic scaling. So you can create more easily kind of a buildup of correlations. I think that, up to now, there's only one paper that has looked into this, which I've kind of yet the opportunity to have read. But also kind of numerics are also quite hard in that case. So this model is quite nice because the evolution preserves Gaussianity of the system. So this means that we can make simulations quite so exact and quite efficient. In that case, numerics would be quite hard, and with analytics, it's already hard to treat the free case as we have seen. So I don't have much intuition, unfortunately, what's happening with the interactions.
Could you explain again this? Could you explain again this SUR versus SU2R issue? So is like the long wavelength physics not pinned down? Is that what the problem was?
So the kind of problem is that I'm not sure at this point that it is a problem, but what's clear is that with this long wavelength physics, what you get is this SUR model, right? Uh, but, but this is kind of an approximation, right? But with the Hubbard like approach, it is really an exact unitary transformation, and this points to a SU2R model. So in this work, they have some comments on this. Um, it is still unclear if this is relevant ultimately. Um, but the crux of it is that you have these two approaches which give kind of two different symmetries in your problem and also dimensionality. And here dimensionality is also kind of important. But so this is the crux. It is still unclear if this is something which ultimately doesn't really matter. But it is certainly there.
So yeah, so it's this Hubbard-like approach was taken by So this is Michel Fava and Adam Nahum, their charge conservation paper that they have down there, right? So they work in like a double space formulation and find this effective non-Hermitian Hamiltonian. This is the paper you're talking about.
No, the um wait. So this is a recent Adam Nahum paper. Yes, they have looked. So they have studied, broadly speaking, the field theory of monitored fermions, and have commented on this. But it's kind of not much more than a comment.
Okay.
A question? So I'm a little confused. Are you studying a 2+1D or 1+1D system?
It's a 2+1D, so it's monitored. So it's a 2D lattice plus time.
So, but the Cadi-Calabrese formula only works for 1+1D, right?
Yes, exactly. Yeah. So the Cadi-Calabrese formula was um, is coming from a 1+1D model. You're right. So the so kind of two things. So first of all, we kind of clearly see this in the numerics, and we don't have an intuition to kind of from the analytics. And this is kind of the boring answer. The perhaps I mean I could perhaps kind of say that since we're looking at these are essentially so these are strips and we have periodic boundary conditions. So this is kind of like taking a section of a torus, right, and increasing its size. Um, so it might be that it looks kind of effectively 1D if we look at the structure, but if we take some other subsystem geometry, for example, a square, and then you have two dimensions which increase. I haven't checked this, um, but kind of the second part of my answer is more perhaps more speculative. The only strictly rigorous answer is that this is what we see. This was motivated from the 1D case of monitored fermions, where numerically it was seen a whole phase with the scaling. And generally speaking, this formula for the entanglement entropy does appear in contexts where you wouldn't expect it to. Um, but I think in the kind of generally speaking, the community there's not a clear understanding of how this or why this pops up, because again, the analytics are generally speaking not so easy.
So
Sorry,
what's the central charge?
the what? Sorry, I can't hear you well.
The central charge, like what's the value?
Ah, the central charge. So what's the value of it, or
Yeah.
so it's the central charge plot is here. So in a from this dotted, so this dashed and dotted line at pi equals pi over 3 is what the field theory in a Gaussian approximation predicts at the critical point. though, and this is the field theory for the Arnes-like approach. So this would be the critical point, which we believe now to be around 5. But the value of the central charge is this. So this is C of gamma times gamma. So you but the gamma is of order 1, roughly speaking. So this is roughly of order 1.
So the nature of the CFT, sorry, the nature of the CFT is a 2 plus 1D CFT that wraps around the cylinder that becomes quasi 1 plus 1D, or what's the...
So my answer before was more kind of speculative on why it might be that we get the 1 plus 1D formula. And my idea is, so what I mentioned is that the geometry that we have here, we're only kind of moving on 1 dimensions, and we have periodic boundary conditions. So this was kind of the idea behind it. But I don't have anything more rigorous than that.
But so it's like a DMRG simulation, or?
This one is it's called quantum state diffusion. Essentially, you take the wave function and just simply evolve it. This is why this kind of approach is nice. So we have a stochastic Schrodinger equation that you can write down quite simply, and then simply by evolving the state themselves, then you have access to everything. So this is exact and efficient.
Okay.
Any more questions?
Yeah, just one more. So this at this extra special point you found, what was the entanglement scaling again? Or does the entanglement not change at all at this? I think you called it a multifractal point.
Yeah, entanglement is still log here.
I see.
Okay. So this is
so actually, what quantity did you like held some signature that like what did you like how did you quantify, like what's special at this point? That's yeah. What did you probe for that?
So for this point, we have looked into this central charge, kind of central charge, quote unquote, or the prefactor of the logarithmic scaling, which is this C of gamma here, and this displays a very sharp crossing point happening here. On top of this, we also had this the multifractality plot, which to me this is really quite surprising. So now, let me emphasize something which I didn't mention. So this is not the result of a fit. So the variance that we get from our numerics overlaid on top, or below the theoretical results with the same parameter coming from the theory. And I don't see why there should be structure a priori here. So why there should be kind of, if you quantify the distance from our data and the theory, why there should be a global minima for any cost function that you define, and why this should be at 2.15. And this does not shift with system size. So we can believe this to be somewhat stable, or kind of quite stable. And this is also a feature that's happening at 2.15. And then the rest towards the end of my talk was still more kind of work in progress and a bit more on the speculative side. And the idea now there is to probe ergodicity in the log phase. So if ergodicity is breaking down and these wave functions still give us a log scaling, but are not ergodic, or so not fully delocalized.
I see. Thank you.
Thanks.
All right. So let's thank the speaker again.